So we will move to our next speaker, Dr. Boohu, online as well. Okay, Dr. Boohu, lecturer at Cardiff University, who will be talking about colloidal quantum dots for indoor and concentration solar cells application. So, Dr. Boo, are you there? You can share your screen, please.
Okay, guys. It should be good evening in China and afternoon in Glasgow. Thanks for the invitation. I'm Bo Ho. I'm a university lecturer from Cardiff University, from School Physics and Astronomy. So my talk is about colloidal quantum dots for indoor and concentration solar cell applications. So here is an image of our Cardiff University main building. It's very pretty, old architectures. So first, I just want to have a very quick introduction about Cardiff, especially school physics. Particularly, I want to draw your attention about this National Center Institute for Compound Semiconductors. So there's a very broad of research about using compound semiconductors in chip factories and also communication applications. So in Cardiff, we're working on different type of LEDs, lasers, detectors, displays, optical communications, solar cells, and also making a lot of integrated circuits device for quantum computing and quantum communication. So there was a very good video. I don't know whether or not I can share with you this because YouTube maybe. Yes, you can.
Compound semiconductors shape our lives. They're behind technologies we use every day, from the phone in our hand to the digital images on our screens. If you're watching this on a tablet, you're relying on compound semiconductors. Silicon is the element used most widely in electronics. But compound semiconductors use elements from groups either side of silicon in the periodic table. Their material properties enable new and rapidly expanding technologies: 5G, aerospace, face recognition, high-speed data communication, imaging healthcare, and the Internet of Things. These applications need a complex combination of atoms. The Institute for Compound Semiconductors, and some of our partner companies, can create the strict growth conditions needed with highly specialist machines called reactors. Funded by the European Regional Development Fund, the newly refurbished ICS Cleanroom provides businesses with the opportunity to exploit state-of-the-art fabrication, characterization, and technology expertise. We take the bare wafer, 4, 6, and eventually 8 inches in diameter. Then we mask it and selectively remove and deposit materials to create structures and devices across the whole wafer. The bigger the wafer, the more devices and the cheaper each CS chip becomes. We then check the functionality of individual devices before they're sent off to the wider supply chain. CS Connected is the world's first cluster for CS expertise. It brings together a host of leading companies along the M4. Our lifeblood is Wales, but our outlook is global. Only through working with others can we grow. Come and join us. We are the home of innovation.
Okay, yes, this is a very short, brief introduction about where I'm come from. I hope you understand these technologies, especially compound semiconductor, is very important materials. So if you do a very quick search in Google and you search keywords like quantum dots TV in PC World, so PC World is a very big retail in UK. You can buy TV and a computer. So you see so many images about a display made from colloidal quantum dots. So quantum dots is a booming up technologies in the world, especially in lighting society. However, there was lack of studies to use it in solar cells. And so to make this kind of material, traditionally, we normally using batch type method using MBE, molecule beam epitaxial growth. And in the last 20 years, there was another field called colloidal chemistry. They can make these kind of nanoscale nanocrystals in a massive kind of yield. And especially they can using continuous flow method to grow a large amount of colloidal quantum dots with different size and different color. So which can well be implemented in either solar cells, LEDs, detectors, and even image sensors. So, and we also can use this kind of colloidal quantum dots to do a lot of material engineering and to changing the size of the materials, to changing the band gap, and also doing the ligand functionations. And even we can do colloidal epitaxial growth to making some super structures based on these small building blocks. There's a lot of research currently carrying on in Cardiff, Cambridge, Oxford, even the rest of the world. I think in China, there's lots of activities on working on this area. So why quantum dots is important in terms of solar cells, especially in this topic about sensors. So why quantum dots is important? So firstly, let's go back to a very basic theory about Shockley quasi limitation. So all the solar cells, no matter the rising star perovskite solar cells or organic solar cells, or the old generation thin film solar cells or silicon solar cells, they all follow this very basic rule with Shockley quasi limitation. So you cannot get an efficiency above 34%. That is the limitation. That is the ceiling. So if you want to improve efficiency in the future, you have to make a very complex structure, like multi-junction solar cells or tandem solar cells, which is costly and very difficult. And if you see the physics behind of this limitation, the main reason for this very kind of small efficiency limitation is because there was three main parameters which was confined this efficiency improvement. The first is about the one electron and the whole pair excited per incoming photon, which means you have one photon, you can only excite one pair of electron holes. Second thing is there was a thermal relaxation of the electron hole pairs, because if you have very high energy photons, the energy which is above over the band gap will be dissipated as kind of thermal heat. And the last thing is most of the solar cells is illuminated by a non-concentrated sunlight. It's just one sun we normally call it. So this is another limitation. And what will be the future for solar cell? In the UK, we all normally need to think about what we need to do the research for next 50 years ahead. It's not something for 10 years or 20 years. We need to think about 50 years later. What will be the future for solar cells? So there was two things we can think about. Firstly, it's about to multiple exciton generation. This is a very simple physics. So when you have a very high energy photons in the bulk, the energy will be dissipated as a kind of thermal heat, as I mentioned, by phonon vibration. So the key physics we need to think about is how to control the cooling rate of lattice vibration. In terms of quantum dots, they have some kind of advantage because of the quantum confinement effect. So the cooling rate is largely extended. So it means you have enough probability to use this high energy electron to excite another pair or even another two pair of electron holes. That is what we call multiple exciton generation phenomenon. And another phenomenon we can consider is the multiple photon absorption. This kind of phenomenon can be normally encountered in laser physics, which called we normally observe this kind of phenomenon called the stimulated emission process. And we can call here a stimulated absorption process. So you have very low energy photons, but they added up together, generate a harmonic oscillation, and then they excited high energy electrons to the conduction band to absorb this kind of multiple photons. That is what we call the multiple photon absorption phenomenon. In colloidal quantum dots, they have very strong multiple photon absorption phenomenon. Recently, we collaborate with Cambridge and Imperial College of London. We did some ultra-fast spectroscopy analysis. We observed this kind of phenomenon in these nanoscale crystals. So we think this is something very interesting, and we are currently working on it to try to improve this solar cell efficiency. So what is the advantage for working on quantum dot solar cell? So actually, if you compare the efficiency of quantum dot solar cell with the rising star perovskite or even the organic solar cell, the efficiency is very low. So the best efficiency reported so far is from a Ted Sargent group in Toronto, which is around 13.5% efficiency. And the efficiency which we reported from UK is which I was reported quite a long time ago in 2013. We got around 9% efficiency in Oxford. And also in MIT group, Mujibor, they initiated this ligand engineering process. They got 8.55% efficiency. So since then, it's very difficult for other researchers to further break through this efficiency limitation, get even higher performance. However, quantum dots have some very unique properties compared to other materials. Firstly, they are inorganic compound semiconductors, which means they are very stable. So you can make this solar cell just in a normal film hood. You don't need a glue box. Second thing is the whole process can be totally solution process. So you don't need any MBE or MOCVD process. And the last thing is this kind of quantum dots can easily manipulate by science and ligand, which give a lot of opportunities for chemistry and physics to engineer the electronic structures. So the typical structure of quantum dot solar cell can normally kind of like assigned in two groups. The first group we call the solid state ligand exchange multiple junction quantum dot solar cell. We call the cascaded junction solar cell. This is normally the method people can get a very stable performance around 9 to 10%. And the second method is using ligand engineering, have a cascaded ligand junction, and you can have around 12% efficiency, which is reported by Sargent group. So you see, this is a typical image of the quantum dot solar cell films after you deposit these nanoparticles on a conducting substrate like FTO or ITO. And then you grow another layers of semiconductor layers of zinc oxide, which also made by a solution process method. And also you can have using the ligand like what I highlight here, tetrobutylaminoiodine, and also 1,2-azone dicyl. This kind of ligand engineering can adjust the band age and also make this solar cell much more stable. So there's a lot of opportunities you can work on quantum dot solar cell to improve the efficiency. And the main working principles you need to do this kind of cascaded junction to utilize this unique size effect and also the band age engineering effect. So where will be the future for next step? So there was two kind of research trend if you look through the whole development of the quantum dot solar cell society. So for the first society is working on concentration solar cells because colloidal quantum dots can be largely reduce the lattice mismatch and also the concentration of dislocations and the defects, which means you can use this kind of material thin films in concentration solar cells after you have a very well-defined concentration optic system. So Henry Smith's group from Oxford and the team which I lead in Cardiff, we report the two of this kind of concentration solar cell based on totally solution process method very recently. And the other way to using this type of solar cells is for indoor solar cell, because there's so many sensors and IoT research, they all need power to they all need energy source to power these sensor networks. So we need this kind of indoor solar cells as a self-powered energy source. There were a few typical papers I cited here. If you're interested, you can have a look later. Because use this kind of indoor solar cell, you can easily to have a sensor network in the room without any physical cable or power source. And this is the reason why quantum dots can be used for the indoor environment, because if you check the spectrum of a typical fluorescence lighting tubes or LED lighting tubes, most of the emission is covered in the visible range, which is the main absorption part of the quantum dots thin films. And also, if we increase the sun concentration like this, this green lines and the yellow line here, you can see they also can be well absorbed by the quantum dots thin films if you check the internal quantum efficiency and external quantum efficiency measurement. And this is also some evidence we observed recently with the collaboration with Imperial College of London. So we found if you're shining a really strong, a very high intense laser with a very low energy, the quantum dot thin films can be completely absorb these kind of strong lasers and generate a massive amount of excitance without any degradation, which means you can use the quantum dot thin films for concentration solar cells. And this is the measurement we did. So we improved the efficiency with a typical 9% to more than 11% efficiency just by increasing the concentration over the sunlight from 1 sun to around 1.5 to 2 sun. You can even to do some kind of very simple engineering to add a convex lens on top of this ITO glass as a kind of simple concentration system. You can easily obtain around 11% efficiency with colloidal quantum dot solar cells. And the stability you can easily see here is more than 10 hours. There's no noticeable degradation. So please do not overlook this kind of efficiency. It's only 11%. It's not a big deal. However, if you think about the future, if we can really improve the efficiency and make quantum dot solar cell work, break 40 or 50 or even 60% efficiency is very, very easy, because you just need one photon to excite the 2 pair of electrons. Then you can get 60% efficiency. So this is one demonstration we did. So we're using this kind of indoor solar cell to power a very simple sensor network. So this is RI detectors, and you can continue to use this quantum dot solar modules to power these IR detectors, which can be used for kind of movement detections. And I believe this is something very promising, and I hope you can join this kind of society to work on this indoor solar cells for power the sensor network. And just a very quick conclusion is in the UK, we can make best performance quantum dots, which above 10%, and which we also got a certification. And also we are trying to understand the fundamental physics and especially the charge transport dynamics within the solar cells and within the thin films. This is the state of art of research in the world. So Toronto is still the leading. They got 13%. MIT is also catch up. They got 9 to 10. And we are also trying to catch up with Toronto, but at this moment we still can only got around 10% efficiency. So there's a lot of things we can do in Cardiff, and there's lots of room we can improve. So I just would like to thank the Cardiff University Royal Society of Chemistry and EPSA for the funding, and my collaborators from Oxford, especially Steve, Andrew, Henry, and also the past members of Sungnam, Jane, and John. And also Cambridge collaborators, Professor Gehan and Sir Mark, Ben, Shiji, and Yurji. These are my past students and postdocs. And also my collaborator from Imperial College of London, particularly Professor James Durant, and Jay Lee and Stoico from Queen Mary Universities. So there's some funded position, PhD and postdoc available in my group. I'm looking forward. If you're interested, you can join my group. Thank you very much. Thank you. I think I catch the time.
Yeah, thank you so much, Dr. Bu. Very interesting talk. So we have time for one question. Any question from people in the room? Any question? Let's thank Dr. Bu once again. Thank you so much, Dr. Bu. So in
Thank you.
interest of time, we'll move to the next speaker. Thank you. Thank you once again.